Mm. So this is if we're keeping this dark green around from up here, and this dark green is in play only if, maybe even if and only if A is the set containing the ordered pair XY, as in there are no other elements. Actually, I'm not sure of the status of that. Let's think about this. So we're saying there exists an X, rather there exists a C such that the set containing his elements X is an element of C, and the set containing his elements XY is an element of C, and C is an element of A. Okay. And now the idea is that, what do I need this dark green for? For all S, if S is not equal to the set containing his elements X, and if S is not equal to the set containing his elements XY, then not S is an element of C. Well, so that's a statement about the ordered pair. The set in question, we might want to clarify that. The set in question is the ordered pair. So I say, yeah, okay, let's start back here. The ordered pair XY is an element of A. If and only if, and this is like typographically replaceable even if not interderivable with, saying that the set containing his elements X, rather the set containing his elements X, and the set containing his elements XY is an element of A. Okay. No, it's the idea. Well, this doesn't tell me that this is the only set. The dark green statement is true. I guess I'm concerned that I would have to step down my biconditional like if I want to retain the biconditional, we have to say, so let's see, if I say C is equal to the set contained, just this set, C is equal to the ordered pair XY, then these two sets are elements of C, but also nothing else is an element of C. So hence having the AND expression. So I suppose the quantifier here would be for all x and for all y. The ordered pair xy is an element of A. Okay. So the complete specification of this set so we'll take it. The complete specification of this set is there exists a C. Well, if I said C is equal to, well, if I and on an expression, let me think here. The second element's x is the element of the set. The second element's xy is the element of the set. There exists a C. Well, if I just say that's C, we could go with let me think here. The set containing as elements x is an element of C. And the set containing as elements x, y is an element of C. And C is an element of A. Huh. And dark green. So one question we could try to resolve here about quantifiers. If I say let's see. There exists a C such that phi is an element of C and lambda is an element of C and C is an element of A. Yeah, quantification should be outside of like this. Okay, and we close this off. And the question is, are we willing to say that that is interderivable with the expression let's see, phi is an element of the set containing can't we? Why can't we get this to work? Let's see. Notebook management. Get that out of there. Let's see. So I specifically say phi is an element of the set containing as elements phi lambda, and lambda is an element of the set containing as elements phi lambda, and C is an element of A. Rather specifically, the set containing its elements. It's an element of A. Okay. Now what is the idea? Okay, so now the question is this a biconditional or is this a conditional expression? This would have to be conditional, right? Now, on the other hand, if we said, so we'll call this case A, I suppose. Yeah, we're running out of color schemes. Yeah, this actually would be best handled by the binary anyway. Alright, so if I instead say, let's hold off on that. Okay. Mm-hmm. Now I think that would be biconditional, and that would be saying that so well, no, that can't be right. That can't be biconditional. And the reason is that if I said that dot 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 is equal to gamma, then our antecedent here I thought I was going to be underlining this with orange, but now I don't see why I would be doing that. Let's see. Right, so I would have phi is an element of the set containing as elements phi, lambda, and gamma, comma, dot, dot, dot. And dot, dot, dot. And gamma is an element of the set containing as elements phi, lambda, and gamma. And dot, dot, dot. And this critically is going to get and collapsed. Or carried along with us. Yeah, well, we would have to and collapse it at some point because it's not in the final expression. And that and collapse would be attended by a conditional forward, not a biconditional. A problem. Is that a problem? Let me think here. Well, the necessity for the biconditional comes out of this belabored practice of using the axiom schema of separation. We're saying there exists a B such that for all x, x is known to B if and only if if x is an element of A and phi of x. In this case, x is an element of the big union of A, and the ordered pair xy is an element of A. Okay, so this biconditional, what are we doing with it? Well, we might be able to get... I guess the idea is that the B in question is the set, is the, this set. Yeah, that's confusing. Hold on, let me go back to the book. What are you thinking, book? I'm not following this reasoning. Let me think here. Actually, we could switch over. We do like a lot of calculus today. I guess we need to do that occasionally because we're making such slow progress. Well, we're making slow progress through everything. That can't be an excuse to do anything new, unless we decide to shelve something completely. Okay, so we're trying to say... We're trying to prove that... Yeah, well actually we don't have a good idea of we don't have a good idea of how to think about this. What do I mean? So this is... There exists a B such that for all x, x is an element of B if and only if x is an element of the big union of A, and there exists a y such that x, a, y. Now, we can't get this biconditionally. I mean, even reasonably so, not merely sort of constrainingly so. this expression is not biconditional with this expression. Okay. Now the point is that this goes one way. We get a conditional forward. Let me think here. So what am I trying to think of this? So we have a biconditional. On one side of it, we can conditional forward into a collapse, into a collapsed expression. Which the point here is that anytime I have this statement, there exists a y such that the ordered pair xy is an element of A, I can derive forward this expression that x is an element of the big union of the big union of A. Says it where I can and this on wherever I have an instance of this, I can and this on forward. I can and it on forward. Though that would cause us to step down the entire expression. Yeah, and I still don't know if that's a problem or not. Back over here, what we're asking is, actually rather, back over here. Right, so we can get the required expression out of this, again, though, only by stepping down. And the point here would be that no matter how many of these gamma, these dot 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 elements we have, we can at least step down into this expression that phi is an element of C and lambda is an element of C. Or alternatively, again, we could and on the forbidding expression that nothing else is an element of C, but then we would have to drop that and once again that would step down our conditional according to our rules. Okay, so but what do I want to do with that biconditional? Or rather, what do I want to do with the step down conditional? Well, so the point is that S is an element of the set containing is elements X, and the set containing is elements X, Y. No, that's not what we want. point is more like if I have the set lying around, the set containing the set containing its elements x and the set containing its elements x, y. Okay, if I say that this thing is an element of A, yeah, well, that's where we're getting our existential statement. I'm getting confused here. What is the point of this excursion? So up here, we're saying phi is an element of the set containing its elements phi and lambda is an element of the set containing its elements phi and lambda. Right? And we judged that this biconditional was unjustified. It doesn't fall out of well, this is a tautology. We, at any rate, could treat this as a tautology, and then we'd be able to put this on whenever we want. But wouldn't the point anyway be to go in the other direction? What do I mean? So I say the set containing its elements phi and lambda is an element of A. Okay, and as it were, I quote myself as saying that. And I get out my string manipulator. Alright, so phi lambda is an element of A. Okay, well, actually, hold on. So this might give us a hint as to what we should do with this biconditional. What do I mean? Do I want this to be biconditional? Where I say phi is an element of the set containing its elements phi and lambda is an element of the set containing its elements phi and lambda, and the set containing its elements phi and lambda is an element of A. Do I want that to be crosshatch biconditional, or do I want that to be crosshatch forward, or even do I want that to be crosshatch backwards? And yet I am thinking I want this to be biconditional. Why? Well, it's like if I stepped this down to condense the expression, and then I get to the other side, I say P then P. P and Q and R and P, then P. Okay, and the point is that I can unpack on the other side. If I say C is equal to the set containing its elements phi and lambda, and then I say then, and this has to be stepped down, then phi is an element of C. C. Well, because there would be two possibilities here. If I had C is equal to the set containing these elements phi lambda if and only if phi is an element of C and lambda is an element of C, and for all S is not equal to phi and S is not equal to lambda, then not S is an element of C. Okay, I kind of ran out of room, but whatever. Okay, so the point here, though, is that this would be part A. Okay, let's call this a notebook management error as well, and we'll indent. How about that? We'll indent to indicate. Yeah, let's make that and part of the notebook management error. And for all S, if S is not equal to phi and S is not equal to lambda, then not S is an element of C. Okay. And the point is that this addendum, case A, if I instead had C, well, yeah, we could do this, and now we say phi is an element of C and lambda is an element of C. And then here, yeah, we need to go to the next line again. And rather, this will be there exists in S. Such that S is not equal to phi and S is not equal to lambda, and S is an element of C. Okay. Let me think here. Why am I doing the conditional in this direction? Right, so the point is that the point is highlighted by putting this here. So we're saying this has to be a conditional forward because there's simply no additional expression. Oh, actually, the comment really should be here. This is empty. That would be what we color underneath. Okay. Yeah, if we adopted a sort of Yeah, well, if we have this expression alone, it's not clear. Let's see. We could say. Yeah, right. I think the point would be we say C is equal to the set containing as elements phi and lambda. We can step that down into saying that phi is an element of C and lambda is an element of C, but we can do the same thing if C is equal to the set containing as elements phi, lambda, and gamma. Why that assemblage of Greek letters? Don't you have favorite Greek letters? Let's see. So neither of these, this expression alone can't conditional backwards because it's not clear which of these two we would conditional back into. Now the question is, so we're saying the set containing as elements phi and lambda is an element of A if and only if, by crosshatch biconditional, phi is an element of the set containing as elements phi and lambda, and lambda is an element of the set containing as elements phi and lambda, and the set containing as elements phi and lambda is an element of A. And the point is that you can and on a tautology whenever you want, and both of these expressions are tautologies. Alright, these, yeah, I mean, I think what we're trying to get at is that these expressions are tautologies. So when we say C is equal to the set containing as elements phi and lambda. Okay. Well, no, actually, hold on. I don't really need that routing error, I guess. I instead say, so phi is an element of the set containing as elements phi and lambda is a tautology. As is lambda is an element of the set containing as elements phi and lambda. And so to make a kind of quote here, since we can and on whatever tautology we want, like e.g. for all x not x is an element of A if and only if A is equal to the empty set, and phi is an element of the set containing as elements phi and lambda, because I can derive that whenever I want from the ground. Okay. Now there's a point, kind of Wittgensteinian point here. Oh, for the day when we can get back to discussing Wittgenstein with the interlocutor, if only we had not placed between ourselves mile after mile of road. A Wittgensteinian point here with, let's see. Right, well, we say we have the ability to tautology on, or and on a tautology rather, whenever we want. Okay. Is that really in the spirit of math? What do I mean? If I laid a set definition as a kind of trail, so we have a common practice of theorem writing. We, in fact, have a common practice of theorem solving that we maintain together by solving theorems. Okay, now, if we've united our practices firmly enough, then we sort of unwind, as Wittgenstein puts it, we unwind ourselves into calculation. And then we thereby incidentally find out what the other of us would do if put in front of that calculation. And we can use that to coordinate merely by passing the instructions for the calculation, or merely by passing the theorem, because I know that you'll pass through the same It's like I could encode a message into a theorem solution. I could design such letterings, such variable name selections, that when you pass through the theorem, you end up reading an encoded message in the variable definitions. Whereas if somebody else had a different practice for navigating sets, they wouldn't encounter that word encoded into the message. Okay, now what is the idea? The idea is that unless we similarly have a practice of plucking out tautologies from the air, giving ourselves the ability to pluck tautologies out of the air on a whim to include them into a proof it's like it requires a creative step that we otherwise don't require of each other. I mean that we otherwise don't require. You just have to unwind. You unwind into the theorem, as we put it, whatever that means. You unwind into the theorem. Okay, and you see what you see. I happen to know what you're going to see because I unwind into the theorem in the same way. If I find that the only way to complete a proof is to pluck an and out of the air, pluck a tautology out of the air, I'd have to trust that you too would pluck the tautology out of the air. And I'm saying that if this is a creative act instead of a mechanical act, it might not strike you. Now, I mean, we could have rules, metasyntactic rules. Always try, in this case, to pluck a tautology out of the air. Okay, though if that rule isn't precise enough, it's not going to tell you to pluck this tautology out of the air that you're required to complete this proof. Okay. Be a little bit like if we communicated with books, if we communicated with quotes from books, and I set up a quote, and then you finish the quote, and you realize, that was like a hidden message. You completed the quote. Or rather, I completed the quote and I realized that the critical message that you wanted to convey was the last part of the quote. How clever. Then what? Hold on, I'm trying to make my pencil sharpener stop being broken. Not succeeding. Maybe that worked. Alright, So the point here is that plucking tautologies out of the air is maybe at odds with at least this conception of mathematical practice, which is that it's about coordinating our arrival at a common endpoint. Though, I mean, this is generally a problem with... It seems like this is generally a problem with creative steps. Dust. Well, and the dream of formalism was that you wouldn't have to take any creative steps. Living the dream. Doing mathematics by rote exercise. Yeah. Okay, let's see here. Yeah, I need to be... I need my setup to be less Rube Goldberg. I'm afraid to wipe everything down. I'm afraid to dust everything because I'm afraid... Like this thing is in one of my pencil trays. This thing, if I try to dust, it's off it goes. It's lovely, it's nice. I like glass, I like marbles. But it was sitting in this tray, and now this thing's covered in dust. And then there's also pencils in the tray that are gonna... Oh, it's horrible. I suppose this is a requirement like all others on my time. Yeah, I should probably stick to the practice of having these pencils in trays instead of just out and about. I guess blue greens, we'll go with the greens. Well, and so the what the author is relying on, I think, is a similar point to what we're making here. What do I mean? You can simply rederive it on the other side. Simply, you can rederive it on the other side. Since you can rederive it on the other side, you don't have to carry it with you. You can and down and then get it back. You can go in either direction. You can and down and then get it back, or you can have it... Rather, you can and down and get it back, or you can lack it, get it back, and then and down. I'm messing this up. But the point is merely that in this case, this tautology of saying phi is an element of the set that contains phi and lambda, we can get that back on either end of this biconditional expression. So this should be biconditional. Okay. And the author's proof relies on a similar point, I think. It's green running out of green. A new reservoir of dust. One moment. What do I mean? Let me see here. So this stretch here is showing that there exists a B such that X is an element of B, namely the big union of the big union of A. Now this is saying there exists a B such that for all X, X is an element of B if and only if there exists a Y such that X A Y. This is observing that because we can derive the expression the big union of the big union of A, rather that X is an element of this big union of big union of A, from there exists a Y such that the ordered pair XY is an element of A. Well, at least we get the conditional in this expression, in this direction, as in we start with there exists a Y such that the ordered pair XY is an element of A. We get that there exists a B such that X is an element of B because X is an element of the big union of A falls out of this expression. Okay, why does it... so all we're doing is... rethink. Yeah, I'm not sure I follow this, because I still don't get how we're getting the conditional in the other direction. we're saying X is an element of B, then there exists a Y such that X A Y. Well, no. So I mean, one point here would be if we thought this was telling us that. Oh, look at this workspace and how organized it is, and how dust free at this point at last. Let me see. So if we took here. So there exists a B that is equal to the set containing, rather, that is equal to the big union of the big union of A, such that for all X, X is an element of B if and only if the ordered pair XY is an element of A. Okay, which turns into X is an element of the big union of A if and only if the ordered pair XY is an element of A. Okay, that's what is confusing. Why does this conditional go in this direction? It doesn't seem like it should. Why? Because if instead A was equal to the set containing as elements, the set containing as elements X, then X is an element of A. No. X is an element of the big union of the big union of A, rather. And not the ordered pair XY is an element of A. Okay, and what that tells me is that the conditional doesn't appear to go in the forward direction. There must be something we're missing, or the author is missing. I feel like the author has pulled one or two fast ones on us already in this book. Could be trying to pull another one on us. I think I'm misunderstanding what the problem is that is solved by reaching this line. And the problem that's being solved here has to do with the explicit expression of the axiom schema of separation. And where is that? There exists a B such that for all oops. There exists a B such that for all X, X is an element of B if and only if X is an element of the big union of the big union of A, and the ordered pair X, Y is an element of A. Okay, That's the expression we have for some reason. However, that's not the axiom scheme of separation. No, instead, to continue with the axiom scheme of separation, we're saying there exists a B such that for all x, x is an element of B if and only if x is, no, rather phi of x. X is an element of A and phi of x. Okay, so if we do this coloring again, the coloring we get out of this is red, red, x is an element of B, x is an element of B, x is an element of and then, okay, now B, B, okay, now A, okay, and now, should have used poppy red. Yeah. Let's see. Okay, now one scary bit here is that well, I wonder if the author's not trying to turn that around. What do I mean? Well, a different reading here. Let's see. Yeah, this kind of thing. Yeah. Let me see. It just makes it harder to read with like a little bit of forethought would. Yeah, well, also a little bit of afterthought. If this were computerized, it'd be really easy to swap these two lines. Not for nothing. Yeah, though also there's something to be said for like I could tear these notebooks apart, frame all these sheets of paper, and look insane. You know how fun that would be? It would be quite decorative. All my life I wanted to be like those crazy people in movies. Crazy TM who have stacks of notebooks filled with arcane symbols. Let's see, there exists a B such that for all x is an element of B if and only if the ordered pair x, y is an element of A and x is an element of the big union of A. Actually, I don't like using the word crazy, admittedly. There's a quote that popped into my head one time while thinking about Zizek, the philosopher. And I said, at some point in history, Zizek, you find yourself the only person in the room still telling racist jokes. If you feel me, Zizek. Similarly, find yourself the only one in the room using a disability as a pejorative term. Yeah, well, this isn't. Well. How would we have to think about this? Well, these both get underlined in red at any rate, so. That's why I rapidly said TN. Yes. Let me see here. So, no, that should not be underlined. Because there's clinical mental problems, and then there's Hollywood. So what would the idea here be? The idea here would be that actually it is the ordered pair xy that is x from the above expression. That a is a, and that phi of x is that. Yeah, but that doesn't make any sense because. Well, because this is you would have to, well, I'm not sure. If we said that, yeah, well, that poses, well, yeah, so then it would be actually, yeah, we could do, let's see here. You know, we spent like 2-3 months solving a LeetCode problem when I was just starting out, and it was horrible. But it was horrible in part because everything was horrible. But this is a little bit like that, where you keep going and it's one error after another. You're petting a porcupine the wrong way, and the porcupine's back extends for a mile in every direction, and you just keep petting it the wrong way. Okay. And this is much like that. This is not getting faster. It's not getting easier. I am getting less and less frustrated. I'd say I'm not really frustrated at all at the moment. Well, frustrated in the sense that my purposes are different now. Right, my purposes are not being frustrated because I changed what my purposes are. Conveniently. For all ordered pairs of the form xy, the ordered pair xy is an element of B, but that wouldn't be right either because that's not what we're trying to get. We're not trying to get that the ordered pair is an element of B. We're trying to get specifically that x is. Because we're talking about the domain, recall, of a function, or a domain of a relation. So the more natural reading would be to say that phi of x is telling us phi of x is equal to the ordered pair xy is an element of A. Okay, but then for one thing, it's a bit off-putting that we have A here and A here, flouting a vague refusal to bind variables in this fashion. It might not be incorrect, but why risk it, you know? Let's see. Formal ontology? Well, it's axiomatic set theory, if we want to call that formal ontology. Sure. Right, so what is the problem here exactly? So we have our axiom schema of separation. There exists a B such that for all x, x is an element of B if and only if x is an element of A and phi of x. And we're trying to look at these three lines and figure out which is the most reasonable interpretation or usage of this expression in this context. In this context, there exists a B such that for all x, x is an element of B if and only if x is an element of the big union of the big union of A and the ordered pair xy is an element of A. Seems to be the most reasonable interpretation, where phi of x is replaced with the ordered pair red y is an element of A and red is an element of the big union of A is... Well, so that also means, though, that the A in question is the big union of the big union of A. Okay, but does that matter? Because the point of the proof, as the author is executing it, is that we can collapse without dropping the biconditional. This is true, incidentally. What do I mean that it's true? I mean that any of these is true. It has the truth value of t. So what is the point? Also, there's something else we could do here if we wanted a little bit of confirmation. Suppose I had the expression P if and only if Q and R, and if Q then R. Actually, in this case, we'd want R then Q. Alright. This is a little bit of meta logic going on here. It's a little suspicious as an inclusion, but whatever. Well, as we said, if you have interderivability, you also can step down that crosshatch biconditional into a forward conditional. But okay, anyway, so this is, what is this saying? So this is interderivable with the expression P then Q and R and let's see, Q and R then P. Okay, and then we're saying and R then P. This looks like it's going to get really bad. Let's see. So, not P or Q and R. Sure. Just rattle this off real quick. Then we'll have not Q and R or P, and not R or P. Okay, and this will be interderivable with, oh boy, alright, not P or Q, and not P and R. And let's see, not Q or not R or P, and not R or P. Okay. Now, what can we possibly get out of this activity? I mean, what can we get out of this calculation? Actually, that's interesting. So if I say that this is hold on. This should be or. Yep. So this has P or not R, and this has not R or P. Is there some kind of simplification we can take here? I think. Actually, yes. We could extract the not R. Okay. So interesting. We should have switched over to calculus at some point already. We'll call this blue. We'll call this brittle. Let's see. Oh, we need that actually. Alright, so we're gonna have blue and not R or P or not Q. And not R or P. And now the idea is to extract the not R's, so this is going to be not R or P and P or not Q. Okay. And blue. And that needs to stay like this. P and P or P and not Q. P or P and not Q. Not sure where this calculation is supposed to be taking us. I mean, yeah, we could distribute all the way. When all else fails, keep distributing. It's kind of horrible, yeah. Well, not R and not P or Q and not P or R. Okay. Or this blue again and indigo, sure. Okay. So if we distributed this not R through, we'd get not R and not P, or not R and R. So that would be a contradiction. So this is going to be not R and not P and not P or Q. Which actually ends up simplifying. So, let me see here. I guess we'll carry that through. That is the wrong color. Yep. This. Let's condense this expression into violet blue for now, make that even easier. Alright, so we're going to have not P or Q and not R and not P or not R and R. Okay. which is a contradiction. Okay, and then we have or, supposing we trust this calculation still after all of this absurdity. Yeah, that's correct. Okay, or violet blue. And now, so contradiction, so this has to be true. Alright, and now we can extract. This parenthesis is wrong. Critically. Here, now we can extract not P. No. Not quite. Let me think here. So we can have not R and not P and not P distributing in the other direction, or not R and not P and Q. Alright, this conveniently and collapses. Oh, the convenience. And we get not R and not P, or not R and not P and Q, which seems like it should simplify, but I guess it doesn't. Huh. Let's see. I'm not sure this is going anywhere. What did we even set out to be proving here? So we have P if and only if Q and R, and then we can derive Q from R. And we wanted to see if that collapses down into anything interesting. Up to this point, it is not. Yeah, we'll leave that trail for ourselves. Let's move on, albeit with limited time. I am a better jazz musician than you are. Probably. Alright, so where did we leave off last time? Okay, so we were trying to parse this question where we're saying, let me see here. Alright, let's start anew. Okay, we're gonna say P of t is equal to 82.5 minus 67.5 times the cosine of pi divided by 6 times t plus t. Okay. And now we were struggling to figure out how to parse this. Why is that? Oh, and we're wondering, when is this equal to 200? Alright. So we say what exactly? T is equal to 117.5, which happens to be these two numbers subtracted from each other, plus 67.5 times the cosine of pi t divided by 6. Okay. But actually, that's not the form we wanted in. Rather, t minus 117.5 divided by 67.5 is equal to the cosine of pi t divided by 6 colon is the same thing as saying that t is equal to, oh no, that's maybe interesting. Maybe not, hold on. No, I don't think that, okay, so we're gonna have the arc cosine times 6, so 6 times the cosine inverse of t minus 117.5 divided by 67.5. Okay, and then divided by pi. Now, one point is that t is equal to this expression, so these two expressions are equal to each other. If we wanted to do anything with that, I don't think we do. Alright, now let's underline this. Okay, this is our equality. What do we want to do with this equality? Well, notably, the cosine inverse of, this is the wrong expression, but I think we can salvage it. Cosine inverse 67.5. Yes, this is why you don't want to use the colon like this here, because you want to use the colon, but this isn't really a comparable expression. Here we can use interderivability. Use that whenever we can, I suppose. And now we're going to have what colon that t t minus 117.5 divided by 67.5. Well, we can't take the arc cosine of anything other than... Okay, hold on, let's say is equal to phi, and now we're saying that negative 1 is less than or equal to phi is less than or equal to 1. Because you can't take the arc cosine of anything other than these. Okay, but so I think I'd make the point here that I think I would make the point here that it makes sense to mod this value down, I think. It doesn't make sense to mod this value down. Maybe. What do I mean? So if I say... Well, so I guess the question is this equal to saying, or is this the same thing as saying the cosine inverse of mod... Oh, I guess, yeah, we can use the symbol, percent symbol. If we prefer to keep our non-idioglyphic, whatever. Alright, T mod, so it'll be T percentage 12 minus 117.5 divided by 67.5. Okay. And now the point is that this is equal to T. Well, no, actually that's not equal to T. We would need these additional modifiers on the expression. The point is that this remains in a legal range. Actually, no, it doesn't. Interesting. Because e.g. if we had T is equal to 12, this would not be a legal expression, so no, this is wrong. Yeah, I don't know what we're gonna get out of pursuing this constraint. I mean, could we like mod 1? What do I mean? So mod 1, now there's something you don't see every day. Let's see. And then we'd have to think about what mod means when you have a negative value. Let's try something different. So the cosine of pi t divided by 6 plus, actually minus t divided by 67.5 is equal to negative 117.5 divided by 67.5. Okay. Now we could try to claim that this is a negligible term, like we thought about yesterday. Though, as we loop through t, this is going to become a less negligible term. Whereas this remains constant. I think we could call this negative 2, for instance. Create some kind of bound to simplify reasoning. Let me think here. Well, so this expression will notably be between negative 1 and 1. An interesting point. Yes, which raises the prospect that we instead render this as is equal to 117.5 plus 67.5 times cosine. I can do that without the bracket. Okay, and this expression remains true. That this value remains between -1 and 1. Okay. So I guess what we're wondering is, let's see here. So if I plug in, let's say A is equal to the set containing its elements 0, 1, 2, ... and pull as required. Yeah, well then we don't really need the set expression, do we? Yeah, whatever. Alright, so now we're going to say 0 is equal to 117.5 plus 67.5 times cosine of 0, which is equal to 1. We've lost a lot of pigment today. So this expression is false. Alright. And now the A point here is that with our red expression, cycling through is going to give us cosine of 0, cosine of pi divided by 6, cosine of ... cosine of in pi divided by 6. Well, t pi actually, but whatever. Which is only informing us that we have integer values for t. Well, we can have integer values for t anyway, and each of them is going to have each such value for t is going to designate a pi/6 position. Okay. And what am I getting out of that idea? So I could target a negative value, e.g. I could choose t is equal to 6 6 is equal to 117.5 plus 67, well, so actually, let's see, yeah, minus 67. .5, which is a false statement. Okay. What about, now 12 loops back around to 1, so we want to loop back around again, so it's going to be 18 is equal to 117.5. What is that, by the way? Minus 67.5. I know this is not correct, but this is 50. Okay. So 20, well, so we're adding 12 again, so it'd be 30, 42. Okay. So if I have 42, t is equal to 42, then we have 117.5 plus 67.5 times the cosine of pi divided by 6 times t. Has some value. Similarly, we add the next 12 and we have 54. T is equal to 54, 117.5 plus 67.5 times the cosine of pi divided by 6 times t is equal to, I should have just done dot dot, but whatever. Alright, let me get on my graphing calculator. And we will say 117.5 plus 67.5 times the cosine of pi divided by 6 times x. Okay. And now what? Now f of 42 and f of 54. Both of these are equal to 50. Ah, of course they're all going to be equal to 50, aren't they? Why is that? Because we're merely cycling back through. Right. Now what? So then it doesn't work to say, for instance, 50. If t is equal to 50 dot dot this would be 151.25 apparently. Yeah, we were so close. And then, so we're descending as we increase. So if I put f of 52. This is equal to 83.75. Okay, if I do 53, 59, 59.04. Okay, 54 drops to 50, so like 53.5. Huh. 53.5 is equal to 52.30. So it's somewhere between these two values. Where t is equal to phi, which is between these two values. Okay, and now if I put in 82.5 minus 67.5 times the cosine of pi divided by 6 times x plus x, and I do y equals 200, and now we put a point over there like we did yesterday. Turn off the first function. Now we have 53.39, which indeed falls in this interval. F of 53.39 is equal to 53.4137, which is approximately what we were looking for. Okay. Interesting. Fifty-three point 53.39. Which is an element of the gibberish set. Yeah, it's either goldenrod or the comment color. I'm not sure. Perhaps I should write something in to mark my uncertainty. Where did comment color go? Carmen, where did I put you? Oh, why would you be in with the reds? I guess that makes more sense than alternatives. Let's see. Okay. Well, that's some analysis. Alright, let's move on. Okay. Next problem. I guess we'll call that some kind of proof. What time is it? Alright, we got time. 35. For the following problems, consider radioactive dating. If I had any X's, I might make a joke here. A human skeleton is found in an archaeological dig. Carbon dating is implemented to determine how old the skeleton is by using the equation YERT, y equals e to the RT, where y is the percentage of radiocarbon still present in the material, t is the number of years passed, and r equals negative 0.0001210 is the decay rate of radiocarbon. Radiocarbon. 99.99 radiocarbon. Alright, so y equals e to the RT. Okay, could have written that a little bit bigger, but whatever. Semicolon r is equal to gibberish, negative 0.0001210. Okay. is the decay rate of radiocarbon. If the skeleton is expected to be 2,000 years old, what percentage of radiocarbon should be present? I see. Y is equal to e to the 2,000 times negative 0.002112110. Okay. Hey, let's find out. E to the 2,000 times negative 0.00210. 0.373 apparently. Or 37.3% apparently. Okay. Find the inverse of the carbon dating equation. Carbon dating equation. What does it mean? If there is 25% radiocarbon, how old is the skeleton? That's kind of a subtle hint that we were in the correct region. I am thinking. Let's see. Y is equal to e to the RT, and now I say interderivable with the natural log of y is equal to RT, which is interderivable with the natural log of y. Let's make a note here that divided by r is equal to t. Should we so desire, we could also say this is 1/8 times the natural log of I, and then say that it's the natural log of y to the 1/8. But we need not do that. We're not required to do that. Okay, so we're saying 0.25, how old is the skeleton? Why would I need to find the inverse of the function, one wonders? So if I say y is equal to e to the r times, 0.25 is equal to, well, it's going to be easier to input this into the calculator, isn't it? And actually, if nothing else, there isn't really a way of putting this into the calculator, I think, right? 0.25 is equal to r times t. Yeah, that's not really amenable to calculator input, interestingly. Alright, whereas this is, because we're going to have, well actually no, it's not either. Yeah, natural log of 0.25, which is imminently interable into a calculator, divided by r is equal to t. I'm coloring this to emphasize that r has a value. Let's see, so if I go back to my calculator, we're saying natural log of 0.25 divided by negative 0.0001210 is equal to 11,456.98. Apparently. Huh. Fascinating. And well, if I put in e to the negative 0.0001210 times x, and we get rid of all of these, then we normalize y to 1. Okay. Uh-oh. And now I have y equals 0.25. Which is considerably lower value than 11,000. Where did we go wrong? Let's see here. Did I enter my calculation incorrectly? No. I don't know. Well, calculation has turned out the same way. Yeah, I don't know what that's telling me. Look at my calculations here. E to the negative 0.00012110, times x, Oh, you rascally devil. Alright, now instead we're going to say... Oh, you got me. You got me. Let's see. Natural log of 0.25 divided by negative 0.0001210. No, wait, hold on. So what we're actually asking here is if I have e to the negative 0.001210 times x. if we go look at that point of intersection. You got me. Are you proud of yourself? Alright, we move on to limits. Limits. What are they about? Being in space. Okay. The vision of human exploration by the National Aeronautics and Space Administration to distant parts of the universe illustrates the idea of space travel at high speeds, but is there a limit to how fast a spacecraft can go? A preview of calculus. Limit of a function, limit laws, continuity, the precise definition of a limit. Introduction. Science fiction writers often imagine spaceships that can travel to far-off planets and distant galaxies. However, back in 1905, Albert Einstein showed that a limit exists to how fast any object can travel. The problem is that the faster an object moves, the more mass it attains in the form of energy. According to the equation, mass equals m equals m naught divided by the square root of 1 minus the velocity squared divided by the speed of light squared, where m naught is the object's mass at rest, v is its speed, and c is the speed of light. What is the speed limit? We explore this problem further in example 2.12. Right? The idea of a limit is central to all of calculus. We begin this chapter by examining why limits are so important. Then we go on to discuss how to find the limit of a function at a given point. Not all functions have limits at all points, and we discuss what this means and how we can tell if a function does or does not have a limit at a particular value. Okay. This chapter has been created in an informal, intuitive fashion, but this is not always enough if we need to prove a mathematical statement involving limits. The last section of this chapter presents the more precise definition of a limit and shows how to prove whether a function has a limit. Let's see. Right, learning objectives. That's okay, 7 sections. Alright. Learning objectives. Describe the tangent problem and how it led to the idea of a derivative. Explain how the idea of a limit is involved in solving the tangent problem. Recognize a tangent to a curve at a point as the limit of secant lines. Identify instantaneous velocity as the limit of average velocity over a small time interval. Describe the area problem and how it was solved by the integral. Explain how the idea of a limit is involved in solving the area problem. Recognize how the ideas of limit, derivative, and integral led to the studies of infinite series of multivariable calculus. And multivariable calculus, rather. Okay. Let's go. As we embark on our study of calculus... As we embark on our study of calculus, we shall see how its development arose from common solutions to practical problems in areas such as engineering physics. Like the space travel problem posed at the chapter opener. 2 key problems led to the initial formulation of calculus: the tangent problem, or how to determine the slope of a line tangent to a curve at a point, and the area problem, or how to determine the area under a curve. The tangent problem and differential calculus. So 2 key problems led to the initial formulation of calculus: the tangent problem, so how to determine the slope of a line tangent to a curve at a point, and the area problem, how to determine the area under a curve. The tangent problem in differential calculus. Rate of change is one of the most critical concepts in calculus. We begin our investigation of rates of change by looking at the graphs of the 3 lines f of x equals negative 2x minus 3, g of x equals 1/2 x plus 1, and h of x equals 2, shown in figure 2.2. Okay. The rate of change of a linear function is constant in each of these three graphs, with the constant determined by the slope. Makes sense to me. And now we can imagine placing curves relative to all of these lines such that the curve only touches the line once, locally. Let's see. As we move from left to right along the graph of negative 2x minus 3 over here, we see that the graph decreases at a constant rate. For every 1 unit we move to the right along the x-axis, the y-coordinate decreases by 2 units. This rate of change is determined by the slope, negative 2, of the line. Similarly, the slope of 1/2 in the function g of x tells us that for every change in the x of 1 unit, there is a corresponding change in y of 1/2 unit. The function h of x equals 2 has a slope of 0, indicating that the values of the function remain constant. We see that the slope of each linear function indicates the rate of change of the function. Okay, indeed. Compare the graphs of these three functions with the graph of k of x equals x squared. Figure 2.3. The graph of k of x equals x squared starts from the left by decreasing rapidly, then begins to decrease more slowly and level off, and then finally begins to increase, slowly at first, followed by an increasing rate of increase as it moves toward the right. Unlike a linear function, no single number represents the rate of change for this function. We quite naturally ask, how do we determine the rate of change of a nonlinear function? Yeah, we quite naturally ask, could I instead be reading Apostle, which is denser and more challenging? We haven't given it a shot in a while. Yeah, let's just keep going for today. Think about it. The function k of x equals x squared does not have a constant rate of change. No, indeed, the rate of change changes over time. We can approximate the rate of change of a function f of x at a point a f of a on its graph by taking another point x f of x on the graph of f of x, drawing a line through the 2 points, and calculating the slope of the resulting line. Such a line is called a secant line. I see. Why is it called that? Figure 2.4 shows a secant line to a function f of x at a point a f of a. Okay. Slope of the secant line is equal to f of x minus f of a divided by x minus a. Indeed. Okay. We formally define a secant line as follows. So am I in the right camera? Yeah, okay. Secant to the function f of x through the points a f of a and x f of x is the line passing through these points. Its slope is given by the slope of the secant is equal to f of x minus f of a divided by x minus a. Okay. The accuracy of approximating the rate of change of the function with a secant line depends on how close x is to a. I see. That's actually, it's more complicated than that, right? Because I can at least draw a graph where that statement is not true until you get close enough. I mean, even a sine wave is a case where that statement is not generally true. It's only true once you get within a period of the sine. And even then, there might be some kind of edge case I'm not thinking about where that doesn't work. Well, yeah, I'm within a period. No, yeah. Because if I start at the beginning of a sine wave, the slope is maximally positive. It levels out to 0 and then decreases. And then re-increases again. Okay, well then actually, yeah, the re-increasing again point there is a problem. Let me pull up a sine wave in the graphing calculator. Sine of x My computer. What have I done? Hold on. Let's see. Alright, now, so this claim that the slope gets closer, right? So if I draw a line, let's scatter some points. Actually, yeah, we could just do that. Let me see. And then I'm going to choose a point over here. And I'm going to give myself quite a good approximation. Alright. Now what is the idea actually? Yeah, that's fine. There. Get my pointer. Alright, now what is the idea here? So the slope of this line is quite close to the slope of the other line over there. Now it's getting farther away. It keeps getting farther away. It keeps getting farther away. And actually, it doesn't get... It starts getting closer again, but then it doesn't get closer than it originally was. So we'd have to move the point B as well, except that the point B is fixed in this case. Let's see. We'd have to bring both points closer. And now we get the similar curve. Alright. The accuracy of approximating the rate of change of the function with a secant line depends on how close x is to a. I might be misunderstanding what would constitute a demonstration in this case. The accuracy of approximating the rate of change of the function with a secant line depends on how close x is to a. As we see in figure 2.5, if x is closer to a, the slope of the secant line is a better measure of the rate of change of f of x at a. Okay. As x gets closer to a, the slope of the secant line becomes a better approximation to the rate of change. Okay. Secant lines themselves approach a line that is called the tangent to the function f of x at a. The slope of the tangent line to the graph at a measures the rate of change of the function at a. This value also represents the derivative of the function f of x at a, or the rate of change of the function at a. The derivative is denoted by f of a, f prime of a. Differential calculus is the field of calculus concerned with the study of derivatives and their applications. Example 2.1 illustrates how to find slopes of secant lines. The slopes estimate the slope of the tangent line, or equivalently, the rate of change of the function at the point at which the slopes are calculated. Okay. Estimate the slope of the tangent line, the rate of change, to f of x equals x squared at x equals 1. So f of x is equal to x squared, x is equal to 1. By finding slopes of secant lines through 1, 1 and each of the following points. Okay, on the graph. So we're fixing one of the points at 1, 1. So if we this, we're going to have, okay, and 1, 1 will be somewhere around here. Alright, which So f of 1 equals 1. Okay, f of 2 equals 4. F of 3 halves is equal to 9/4. Okay, so 2 would be somewhere over here, and then 3/4 would be, okay, that's actually not where 2 would be. This rockets off into the stratosphere with astonishing rapidity. Where would that be? Let me see here. Yeah, I don't know if we're gonna make it. Yeah, but also. It doesn't look like our graph intersects that point. Yeah, we need to increase more slowly. Okay. Sure. Okay, and then in between these points, something like that. Though 9/4, this is, yeah, it's a little bit over 2. That's roughly correct. All right. I don't know what camera I was on, but whatever. All right. So now what is the idea? All right. So if I have right, so we're gonna have 4 minus 1 divided by 2 minus 1 is equal to 3. Well, 3 divided by 1, which is equal to 3. Okay. And now I'm going to have 9 divided by 4 minus 1 divided by 3 halves minus 1, which is equal to 5/4 divided by 1/2, which is equal to 10/4, which is equal to 5/2. Okay. So apparently these are the slopes at these two positions. Okay, let's confirm. Yeah, that is correct. All right. The point in part B is closer to the point 1, so the slope of 2.5 is closer to the slope of the tangent line. A good estimate for the slope of the tangent would be in the range of 2 to 2.5. Where am I getting the value of 2 from? Estimate the slope of the tangent line, rate of change, to f of x equals x squared at x equals 1. Okay. So we have these additional points. Well, no, this additional point, rather. Alright, so we will have 25 divided by 16 minus 1 divided by 5 fourths minus 1, which is equal to 9 divided by 16 divided by 1 divided by 4, which is equal to 36 divided by 16, which is equal to 18 divided by 8, 9 divided by 4. Okay, I believe it. We continue our investigation by exploring a related question, keeping in mind that velocity may be thought of as the rate of change of position. Suppose that we have a function s of t that gives the position of an object along a coordinate axis at any given time t. Can we use these same ideas to create a reasonable definition of the instantaneous velocity at a given time t equals a? Yeah, so it would seem. We start by approximating the instantaneous velocity with an average velocity. First, recall that the speed of an object traveling at a constant rate is the ratio of the distance traveled to the length of time it has traveled. Okay. The speed is the ratio of the distance traveled to the length of time. Duration of time, you might say. We define the average velocity of an object over a time period to be the change in its position divided by the length of the time period. Okay. Let s of t be the position of an object moving along a coordinate axis at time t. The average velocity of the object over a time interval closed on a to t, where a is less than t, or closed interval on t to a if t is less than a, is v average is equal to s of t minus s of a divided by t minus a. Alright. As t is chosen closer to a, the average velocity becomes closer to the instantaneous velocity. Note that finding the average velocity of a position function over a time interval is essentially the same as finding the slope of a secant line to a function. Makes sense? There's really just changing labels, if anything. Furthermore, to find the slope of a tangent line at a point A, we let the x values approach A and the slope of the secant line. Similarly, to find the instantaneous velocity at time A, we let the t values approach A and the average velocity. Let me think here. Slope of the tangent line, we let x values approach A and the slope of the secant line. Okay. Kind of a strange phrasing, isn't it? I mean, the slope of the secant line is going to be equal to the entire expression. So, in the slope of the secant line. Similarly, to find the instantaneous velocity at time A, we let the t values approach A and the average velocity. This process of letting x or t approach a in an expression is called taking a limit. Thus, we may define the instantaneous velocity as follows. For a position function s of t, the instantaneous velocity at a time t equals a is the value that the average velocities approach on intervals of the form closed interval from a to t and closed interval from t to a as the values of t become closer to a provided such a value exists. Example 2.2 illustrates this concept of limits and average velocity. Finding average velocity. A rock is dropped from a height of 64 feet. It is determined that its height in feet above ground t seconds later, for 0 less than or equal to t less than or equal to 2, is given by s of t equals negative 16t squared plus 64. Okay, we could factor out the 16, you know. We could have negative 16 times t squared plus minus 4, rather. Find the average velocity of the rock over each of the given time intervals. Use this information to guess the instantaneous velocity of the rock at time t equals 0.5. Okay, so now what is the idea? Yes, speaking fast, did we absorb the material fast? Oh, will you look at that? We're out of time. It doesn't matter what this means. All right, I'll be back tomorrow. Have a good one. See you soon. We will try to churn through calculus with aplomb. Unless I decide that working on calculus is an unworthy activity given my station in life, which requires maybe more effort to accumulate a job. Anyway, see you soon. Have a good one.